So we're going to look at lesson 3.3, which is the differentiation formulas, so that we can get shortcuts to some of these procedures that have been taking us a while. So first off, let's think about our slopes of our tangents and how they relate to a graph. So let's look at our constant graph. So like if you look at this graph, we know that a constant, the slope is 0. So no matter what, if we have a constant function, the derivative is always 0. So you don't have to go through this procedure. You should know from now on that the derivative of a constant equals 0. It's a rule, it's a fact, and then if you know that fact, you don't have to plug it into a formula. It's been proven kind of right there. And we've been talking about this before, so some of these will not come as any surprise to you. It's just kind of a matter of formally saying that, okay, every time we have the derivative of a constant, we always get 0. So that's exactly our rule that you want to remember, that the derivative of a constant is 0. So if we have f of x equals 7, we know that the derivative of f is 0. And it will always work like that no matter what the constant is. Whether they call the constant c, whether they call the, they've actually named the constant to be some particular number, it's always going to work like that. Now, we obviously, that's not the only type of functions we've come across. We've come across lots of different types of functions. So we're going to need to look at some other types of functions. And the first ones we're going to deal with are power functions. So we're going to deal next on the next slide with power functions. So our next functions we're going to be looking at is what happens if our function, and I'll write a little bit bigger here, is f of x equals x to some power. So first let's look at when f of x equals x. Well, for those, we know that the derivative of that is 1 because the slope of that line is 1. So if we're tangent, there's no other way to touch that line except to be equivalent to that line, so the slopes would all be 1. So we can say that the derivative of x in terms of x is 1. But what if our power gets higher? Well, if we are taking the derivative of x squared, if we went through that entire process of our difference quotient and we did the h approaches 0 in all our formula, you get 2x. If our power is cubed, you get 3x squared. Does anybody see what's happening to our power as we go through this process? So every time we do this, our power drops by 1. And what else happens?
Do you move the exponent in front of the...
Yes. So what happens is look at our x squared here. The square dropped down in front and the power reduced by 1. The cube dropped down in front and the power reduced by 1. So what happens is no matter what the power function, look at our 4. The 4 dropped down in front and the power went down by 1.
It's like a pattern?
So it's a pattern, and the rule is, and I'm going to write it more clearly on the next page, but the rule is if we have a power function, so just a standard f of x equals x to the n, the derivative will always be, drop the n down in front, take your power and minus 1. So that's our rule. That pattern follows anytime you have a power function. So if you did the long way for all of these functions, you would find that pattern is consistent. Even if you have a power up to 100, 1,000, it's all going to do that every single time.
Which is what we found out each time we got the derivative. If you take the derivative of a derivative,
it keeps dropping the power the more derivatives we take, correct. Now let's show that. I think on the other slide they do it a little more formally. So that's what that says right here, that if you take the derivative in terms of x to the n, you always get n times x to the n minus 1. So that's just repeating that rule that we discovered was happening on the last slide. And that occurs when our power is any number, whether it's a fractional power, whether it is a negative power, a positive power, it doesn't matter. It always drops down in front, and then the power goes down by 1. Now, this just allows us here that if we have a constant, that we can pull that constant out in front. So a constant just can go along for the ride, and so the constant times a function's derivative is the same as the constant times the derivative of the function. So let me show you what that means. So let's say we are taking the derivative of a constant times, let's say, a power function that we just learned about. Well, the derivative of that is just 7 times the derivative of x cubed. Now, what's the derivative of x cubed? Well, we already learned that. The derivative of x cubed is just 3x squared. So the 7 doesn't affect the derivative of the x cubed. It just multiplies by it, and so then you would get an answer of 21x squared.
Can you explain that again?
So if you have a constant in front of a power function, you use the rules for the power function like you always do, and then you just multiply that final answer by whatever that constant is that was sitting there.
Okay.
So that 7 just kind of keeps coming along for the ride, and it multiplies by the derivative of 3x, or of x cubed, which is 3x squared. So constants don't really affect those rules. They just keep coming along, and that constant will multiply by whatever you have as an answer. Now, because of our limit rules and because of some of, these are limits, remember, that's where they started from. If we have two functions that are added together that we want to take the derivative of, we can take the derivative of each individual piece. So each term we can differentiate separately. That's what this sum rule means. So let's say we have a function like, let's say our function is x squared plus 3. We can take the derivative of this function by taking the derivative of x squared plus the derivative of 3. Well, the derivative of x squared is 2x. The derivative of the constant 3 is 0. So because those two things are added together, we can just take the derivative of each individual term that is added together. So this allows us to do those polynomials. Remember when we had polynomials we were doing, and it was something like x squared plus 3x minus 6, and we had to do the difference quotient in those? That became very complicated because we had that x plus h had to go in lots of pieces. This requires us just to know the power rule for each individual term. And then we can apply the power rule each time and go from there. The same thing applies for subtraction. That just means if there was minuses between them, you could do it with minuses. So let me show you a little example of a minus. So if we have something like our function, let's say, is 5x squared minus 2x plus 6, and we were taking the derivative, we would take the derivative of each individual piece. So it would be 5 times 2x minus 2 times 1 plus 0. And see how quick the derivative is now compared to when we had to do the difference quotient. It becomes a much nicer thing to do the derivative of compared to what we were doing in the past. So we can do very long, complicated polynomials very quickly. And if you can ever rewrite something as a power function, like square roots, write it as a power. And that's why we looked at power functions in pre-calc, so that we could really kind of identify, oh yeah, that's a power function, and then I can use my power function rules. So we're going to do some examples next. So let's look at example 1. We've got 4 different ones we're going to practice. So you'll notice, for example 1, we have power functions for each of these. Now they use different notation, but each one of these, they're just saying, hey, what's the derivative? So example 1a, they're finding the derivative of x to the 6th. That's what that little prime notation right there tells you. Hey, do the derivative. And so what should happen to the 6?
6x.
Comes in front, and then the power does what?
It goes down.
It drops down by 1, and so now that becomes a 6x to the 5th. Perfect. Let's do b. Even for a power as big as 1,000. And that y prime is just another notation for saying, hey, take the derivative of y in terms of x. And so that means drop that 1,000 down in front. Power goes down by 1. C, same notation. dy dt means take the derivative of y using t as your variable. And so here, what happens to the t? Well, the power drops down in front. The original power drops down in front, and the power goes down by 1. This just, part D says to take the derivative of r. So the 3 drops down in front, and then we have r squared.
So what was the different ways of saying take the derivative?
Yeah, so all those are just showing you the different notations that you might see when it comes to the derivative. And if your variable changes, you'll notice the bottom, if you use that dr dt or whatever, those things, the bottom will indicate the variable that you're differentiating. Now, let's take a look at these ones. Now, before we do these ones, we want to write them as power functions. So you would want to write this as an x to the negative 2 power function. because it's in the denominator, you can flip it up and make it a negative exponent. Then we can use our rules for power functions. Right before that, we would go, I'm not sure what to do to it. But as soon as you write it as a power function, you can use the power function rules. So the derivative, you just drop the negative down in front, and then we get an x to a power that goes down by 1. Now be careful. What is negative 2 minus 1? It's negative 3. So that is your answer. Sometimes you'll see that answer rewritten back as a fraction. That would flip your x down below. I'm okay with you leaving your answer as a negative exponent, but please be aware that there are times where maybe if you're checking your answers in the back of the book, you're looking at a multiple choice, they might write your answer as a fraction again. Okay?
So we just have to know how to flip it back to the
Yes,
fraction.
so just make sure that you know how to flip it if that happens. Now let's take a look at this. Last year we talked about radical functions and how to write them as a fraction. So remember, this number here is your index. That's going to be your denominator. This number here is your power. That's going to be your numerator. So it's going to be x to the 2/3. As soon as you write it as that power function, then you can use your rules that we know happen with power functions. So y prime in this case, or the derivative of y, would be 2/3 drops down in front, and then the x becomes 2/3 minus 1. Now let's remind ourselves how fraction works. 2/3 minus 1 is the same as 2/3 minus 3/3, or negative 1/3. So this could be written as 2/3 times x to the negative 1/3. Now I just want to take a moment to talk about that kind of notation there. That's really the same as that. So that's one way your answer, I'm okay with this being your answer, but note that you could write it like I just did. There's actually another way as well. I'm sorry, that bottom number here in front, that should be a 3. Yeah, okay. Another thing that you should think about is rationalizing. We would need 2 more x's to make that be a pure x down in the bottom. So it would be 2 cubed root of x squared over 3x. I am not partial to doing that in a calculus class because usually it doesn't help you a whole lot. I like the one in the box, but note, these two are acceptable ways to write your answers if you were checking for a multiple choice answer, like on a final exam or something. You would need to know where they came up with that. And they did it because of rationalization. Because it's a cubed root, that's why we needed 3 of them total in order for it to work. So that's kind of how it works like that. Okay?
Why did you multiply? Like, why is it x squared?
We need 3 total x's to come out of a cube root. And so since we only had 1 x, we need to multiply by 2 more x's to make it a total of x cubed so that we can cube root it. So that's how you rationalize for a cubed root. But you're mostly used to rationalizing for square roots, and that's what you would do for a cube root. Let's look at example 3. It says to find the equation of a tangent line to a curve y equals x square root of x at the point 1, 1. So remember, anytime they ask us to find an equation of a tangent line, we need to know the derivative of the equation so that we can find the slope of the tangent. So I would rewrite this equation as a power function so that I could find the derivative, so that I could just take and drop that power down in front and reduce the power by 1. Now, that is our derivative. Remember, that is going to be the equation for all our slopes of our tangents, and we want to use the 0.11. So our slope of our tangent that we are going to use is 3/2 times 1 to the 1/2, or 3/2. Now, as soon as we know the slope of our tangent and the point involved, you can just use the point slope formula, y minus y1 equals m times x minus x1, to find the slope of our tangent, or the equation of our tangent line, excuse me. So we would put our 1, 1 in here, and then we would put our slope right there. So we would get y minus 1 equals 3/2 times x minus 1. Now I'm okay with you stopping right there. That is the equation of the tangent line. So you're welcome to just stop. Many times, again, the back of your textbook, multiple choices on like an AP test or a final exam, may not put it in that form. So you should know how to put it into like y equals mx plus b form. So I would probably distribute that 3/2 and add 1 to both sides. And so that is the equation of your tangent line. It's not a bad idea if you're doing your homework. You can throw these into Desmos or some type of graphing utility. If you look, here is that equation. That's what y equals x square root of x looks like. It looks like that. And then I just graphed that tangent line, and you can see that it hits it exactly at 1, 1. So you can check these by putting both the original equation and your tangent line equation into Desmos, and they should touch each other at the point that was given, and it should just appear tangent. It should appear like it's just kind of gliding across just that point in the graph. Now, depending on the shape of your graph, sometimes it will hit another point in the graph, but you're just looking relative to that spot, is it a tangent line? Let's do another one. So here we're just practicing. So here for number 3, or for 4a, we have a 3 that is a constant. We can pull that out in front of the x to the 4th and just take the derivative of the x to the 4th. The x to the 4th follows our power rules. So we are going to drop down the 4 and drop the power by 1, and then just clean it up a little bit. So the answer is 12x cubed. What's our constant in part B? What's on the x? The negative. So you can pull the negative out in front, take your derivative of the x, which is 1, and so then it would just be negative 1 times positive 1, which is negative 1. So get used to, the derivative of 2x is 2. The derivative of negative 5x is negative 5. The derivative of negative 1/2 x is negative 1/2. So x's go away, and you're just left with the coefficient in front. Because think about your y equals mx plus b. I mean, that's your slope anyway. So that shouldn't completely surprise you.
Is that because the x has a power of 1, so just to the power of 0, which makes it 1?
Exactly. It follows power rules. Now look at here. We've got a big polynomial. So let's take a moment and take the derivative. We just are going to do each individual piece. Think about if you had to do the difference quotient for this, and you would have to take that x plus h to the 8th power. That would be ridiculously awful. So now we have a shortcut, and it can even work for nice long polynomials like this one. So this is going to be 8 times x to the 7th plus 12 times 5x to the 4th minus 4 times 4x cubed plus 10 times 3x squared minus 6 times 1 plus 5 times 0. Well, let me put the 5 there. You should take one step to kind of clean it up a little bit, make it a little prettier.
But why is 5 times 0?
Think about our x's there is really, we don't
Constant.
have a 0.
Okay,
It's a
but
constant.
Mrs. Hutton, why were some of them not have X's, like the 10 and then 6?
Because that's the
So
coefficient.
the coefficient is a constant. The coefficients just stay out in front. And
But so like the 12x5.
Uh-huh.
So the 5 goes before the x. Why does the 4 go above the x?
the power always goes from its original power and reduces itself by 1. Okay, so look. The 8 went down in front. The power became a 7.
Okay.
The 5 goes down in front. The power became a 4. The 4 goes down in front. The power became a 3. The 3 goes down in front. The power becomes a 2. The 1, which we don't normally write but technically is there, goes down in front. The power becomes a 0. So that's why we don't have any x's there. And then here the power was a 0, so it becomes a 0.
Okay.
It's a constant.
I was so confused trying to figure out what was happening.
Yeah, and then let's go ahead and make this a little nicer. So we get 8x to the 7th plus 60x to the 4th minus 16x cubed plus 30x squared minus 6.
And we're technically keep on taking the derivative of that until that
you
last
can.
x equals
Yeah.
0.
Let's do another one. It says, find the points on the curve where y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. So remember, if the tangent line is horizontal, that tells us that the slopes will be 0. So you have to interpret that as saying, oh, that means our slopes are 0. So that means our y prime has to be 0. So then we're going to take the equation, x to the 4th minus 6x squared plus 4. We're going to find y prime, which is 4x cubed minus 12x plus 0. And we're going to say, where does that thing equal 0? Where is it horizontal? Because that is the equation for all of the slopes of our tangents. Well, to solve that, you can factor out a 4x, leaving us with x squared minus 3 equals 0. We can use our rules for factoring, or you can just set x squared minus 3 equals 0 when x squared equals 3. So x is plus or minus the square root of 3. And then this piece right here gives us that x equals 0. So those are our 3 points where the tangent lines are horizontal. Another way you could have solved this right here is you can do x plus the square root of 3, x minus the square root of 3. That will still result in 3 answers: 0, negative radical 3, positive radical 3. Now, how do you check it? Well, look at the graph. Those points are the points. We've discussed these with graphs many, many times, that we can find these peaks and valleys if we know where the derivative is equal to 0. So that's kind of how you would do one like that. So that's kind of an introduction to some of the derivative rules for power functions.